Okay, so in this chapter, we'll study motion in one dimension. So let me set this up for you guys. And I have to draw a lot of diagrams just because I'm recording this for online classes. All right, so what we are really interested in is three-dimensional motion. Okay, so you get in your plane and you fly around like that. That's what we're interested in describing. Okay. So the next 2-3 chapters. Now it turns out that, so before we do that, so now here's another simplification. Okay. So, I mean, when you get in your plane, it is an extended object. It's not a point object. Okay. And what we will be looking at is, we will look at motion where every point of the object has the same displacement, same velocity, same acceleration. So we are not looking at motion like this. Okay? So there's no spin to the object. So we'll look at motion where you can treat the object as a point object, as a point particle. Okay. And you can do that when it's not spinning for an extended object. All right, now here's another fact. So when you're flying like that, okay, here's your shadow along the x-axis. Here's the projection along the x-axis moving like that. Here's your projection along the y-axis moving like that. Okay, so we can give you your x-coordinate as a function of time. You see, here's your, and you might know this notation or not, there's your position at time t, okay? And there's your x-coordinate as a function of time, and here's your y-coordinate as a function of time. Here's the projection along the z-axis as a function of time. Okay? Now it turns out that, if you push the plane in this direction along the x-axis, parallel to the x-axis, it won't affect the motion in the y and the z direction. So did you guys understand that? So let's say you were moving along and then you fired jets that pushed you in the x-axis. Whether you fire the jet or not, the motion along the y and z axis are not affected. Yeah. So that's a way of saying that the motion along each axis are independent of each other. Okay. All right, so now then, rather than doing that, rather than describing the three-dimensional motion, what we'll do is, here's how we'll do it. And I like to say it this way, you eat a steak one bite at a time. So what we'll do is, we'll start off by describing motion in one dimension. Okay? We'll learn to take this little baby step. And then what would be the next thing? Then combine the three guys to get a three-dimensional motion. Okay? And so we'll do that over the next 2-3 chapters. Okay? So for now, we'll just describe motion in one dimension. Okay? So that's how we'll start off, and that's what this chapter is about. Okay? So an object is moving along a straight line. Okay? And we want to see how we describe that. So here is an example. So for instance, here is a straight road. And again, like I said, we are going to, in one dimension, we won't let this road curve. If the road curves, it could be a 2 or 3-dimensional motion. Okay. So here's a motion. This car goes forward and then goes back like that. And it's doing whatever it is doing. It's choosing to do. Okay. Now the question is how best to describe this motion. Okay. Anybody want to take an attempt at describing this?
Car move forward, I think, was it 30 degrees?
Right.
Quite numbers. And then
So you guys understand how, a description like that might go on and on. So over time, we've learned that the most useful way to describe a motion is what we want is, okay, so what we do is, along this road, we draw an axis, there's the origin. We're going to refer to your position with respect to that origin. We'll call this the positive direction, that the negative direction, okay? Okay. The most useful piece of information is the location of the particle as a function of time. Okay. That's the most useful, okay? And that's what we want. What we want is the position as a function of time. Okay. So, for instance, here's the three-dimensional position vector as a function of time, and I've already given that to you. There is the x-coordinate as a function of time, y-coordinate as a function of time. This is what we want. When we ask for a description of a motion, that's what we want. Okay? Once you have that, then you can calculate all kinds of stuff that you're interested in, calculating about the motion. So I'll just make up an example. So here's a motion that's okay. And again, we are always working in SI units, so the position is given in meters. Again, distances are measured in meters. So what will the units for this guy be for 7?
7 meters.
It'll be, this entire thing as meters. So this 7 meters per second cube. This has units of meters per second squared. Yeah. So that has units of acceleration. This has units of meters per second. Okay. And so on. So, and this guy has units of meters. Okay. All right, so here's a motion described to you. Okay. And then typically we'll be interested in what is the velocity of the object at a given time. And you will learn in this chapter the velocity is just the time rate of change of the position vector. Okay. It's the time rate of the change of the position vector. Right now, there's no indication of a vector, but that's what that is. Okay. And you guys know how to take the derivative of a function. Okay. Can anybody help me out here? You guys have all done derivatives? Yeah. You haven't done derivatives yet?
I made the top of this
Okay. Huh? You haven't done derivatives either. You have, okay. Who hasn't done derivatives? Okay, so 4. All right, so let's give a 30-second preview of what we'll need. Okay. You guys all know what a function is. Here's a function, okay. There's a couple of pieces of information we use from functions in this class. Okay. So, for instance, what is happening here? As you go to the right, the function is increasing. And what is happening here? The function is decreasing, increasing, it's constant, and so on. Okay, what is a good measure for the increase or decrease of a function? What you can do is, if you want to know what is happening at this point on the function, what you can do is draw a tangent line, and the slope of the tangent line tells you what's happening. If the slope is positive, it's increasing. If the slope is negative, it's decreasing. And the magnitude of the slope tells you how fast it's increasing or decreasing. All right? Well, the slope of the tangent line happens to be the derivative. Yes, so that's a useful piece of information. Yeah. And then you learn how to do derivatives. So for instance, if the function is x to the power n, and you'll get this laundry list, x to the power n df by dx is n times x to the power n minus 1. Okay? And sine x is cosine x. Okay. So that's one function whose derivative itself. Okay? So what does the derivative give you? Very good, my friend. Okay? Now, if you happen to plot the position as a function of time, that slope turns out to be the velocity. Okay? So depending on what it is that you plot. If you're plotting velocity, that's a function, as a function of time, the slope turns out to be acceleration. Okay? So the slope can mean different things depending on what it is that you're plotting. Okay? So the derivative gives you the slope of the tangent line in this one-dimensional case, and that's telling you how fast the function is changing. Okay? And there's another piece that we'll use. This might happen 3-4 chapters later, but anyway. So you have a function like this, and you saw that the rate of change of function is given by the slope of the tangent line. Now the thing we're interested in is what is the area under this curve? Okay. That'll be useful for us. So for instance, if this was force and this is the position, that area will be the work done by that force. Okay. And that area is given by an integral. Okay. All right, so, well, how do you do integrals? Again, you'll get a laundry list. Okay. Actually, and what I'll do is I'll write an indefinite integral. Okay. All right, so this is the beauty of copy and paste. If this is your function, The integral of that function is that. The derivative of this function was that. The integral of this function is that. All right, so if you go in this direction, you're taking the derivative. Okay, so they are inverses of each other. Okay. Well, I'll post the recording. All right, so again, the derivative gives you the rate of change of the function, and the integral gives you the area under the curve. And depending on what it is that you plot, this will have different meanings. Okay? And so those will be using those two tools. All right, going back to our example. So what is this guy? What have I done here? When I gave you this function, what have I done? I've described a motion of some object to you guys. Okay? So when we ask you to describe a motion, what we're asking you to do is give the position of the object as a function of time. Okay? And you give me this, you told me everything there is to know about the motion. Okay? That's all I need. And if I want to calculate the velocity at any given time, I just take the derivative. And again, you guys will be experts before you know it. Okay, so the derivative of t cubed is 3t squared. 3 times 7 is 21. The derivative of t squared is 2t. Okay, the constants just multiply 2t, so 2 times 5 is 10, 10t. Derivative of t is 1 with respect to t, so that's 4. And the derivative of a constant is 0. Okay. So there's the velocity as a function of time. See, you just gave me that thing, and now I know how fast the object is going at any time. And if you wanted to calculate the acceleration is the derivative of the velocity, which turns out to be the second derivative of the position. Okay. So now we're just going to take the derivative of that. Derivative of t squared is 2t, so 2 times 21 is 42t. And then derivative of t is 1, so that's 10. And derivative of 4 is 0. Okay. And generally that's what we're interested in. So what we'll do is we'll ask, so when somebody is asked to describe a motion, this is what we're asking, so that we can calculate the velocity and the acceleration at all times. Okay? And that's pretty much it for the chapter. Okay? You guys understand?
The initial equation, why are you using time cubed? Because that's just showing the relative position of whatever you're tracking at that point. So how are you able to put that in there for that dimension? Better yet, I'm not understanding the initial format of the description of motion.
Okay, so here's a motion, you understand this? Here's a different motion.
That makes sense.
How many different motions are there?
That was 3 different motions.
Yeah, how many different motions are possible?
Are you talking about dimensionally or just ways it can move?
Ways it can move.
So infinite.
Yeah. There's an infinite number of functions that describe those particular motions.
Okay.
Each function is describing one motion. So what is this motion describing? Okay, this motion is telling you that at t equal to 0 seconds, it's at 8 meters. At t equal to 1 seconds, it's telling you 8 plus 4, 12, plus 17, 24 meters, and so on.
Okay, that makes more sense.
Right. Of course it makes more sense. It's mathematics. All right. All right, you guys understand now? So when you're given the position as a function of time, this is a complete description of the motion. All right, that's in one dimension. And soon, like we said, soon we'll be graduating to three-dimensional motion. Okay? So when you're doing three-dimensional motion, all you're doing is giving me three functions, that's all. Yeah? And if you want to describe n-dimensional motions, give me n functions, that's it. Yeah? All right. Any other questions before we proceed? All right, so here was a motion. And really, this is what I'm interested in. And what's done here is, instead of giving me an algebraic form of the function, the author has drawn a graph. This graph and the functional form are equivalent representations. Okay? So you see, this graph tells me where the object is at all times. So at 10 seconds, it was at 50 meters. Okay? At 20 seconds, it's at 38 meters. At 30 seconds, it's at 0 meters. At 40 seconds, it's at minus 30 meters. Okay? And you already saw that if I wanted to calculate the velocity at this point, what do I do?
Take the derivative at that point.
You take the derivative at that point. Or graphically, what you would do is you draw a tangent line, and the slope of the tangent line gives you the velocity, which is the derivative. Okay? If I wanted to calculate the velocity at this point, go there, draw a tangent line, the slope is negative, meaning the object is traveling to the left, and that is true. See, its x-coordinate is decreasing. Okay? So either a graphical representation or a functional form, those are the most useful pieces of information. In fact, this is the most useful piece of information. Okay? You already know what vectors and scalars are. Scalars are just single numbers. They only have magnitude. Vectors are quantities that have both magnitude and direction. Okay. Speed is a scalar. Velocity is a vector. Force is a vector. Acceleration is a vector. Okay. In 3 dimensions, you need 3 numbers to give a vector, specify a vector. In 3 dimensions, how many numbers do you need for a scalar? I'm sorry? 1. In 1 dimension, how many numbers? 1. Okay. In n dimensions, it doesn't matter how many dimensions you have, you just need 1 number to specify a scalar. Okay. So speed, pressure, temperature, they're all examples of scalars. Velocity, acceleration, displacement are vectors. Okay, so now we'll define some of the terms. Again, in this chapter, we are restricting to a one-dimensional motion. So all our objects are going to move in a straight line. How many possible one-dimensional motions are there?
2.
Infinite. Okay. So, all right, so you have to give the location of the object with reference to a coordinate system. Okay. So So this is our axis. We'll draw our origin there. We'll say distances to the right are positive, distances to the left are negative. Okay. So let's say this guy starts off here and moves in that direction. Okay, you give his position at all times. That's what's given here. Okay, so at 0 seconds, the armadillo was there. At 1 second, it was there, and so on. Okay. You know, yeah, this has all the information, but I would rather have this. Okay. But these two are equivalent forms of information. Okay. Mathematically, a motion of an object can be described by giving the position as a function of time. Yeah. So that's how you describe the motion. All right, now we'll describe a quantity. This displacement, it is a vector. Okay. So let me do it in 2 dimensions first, because it's easier to understand. So let's say you go from point A to B, and you go along this path. Your displacement is this vector, a vector pointing from the starting point to the final point. So if you went along this path, what is your displacement? The same thing. Okay. So the displacement is a vector pointing from the initial point to the final point. So in 1 dimension, you can only walk back and forth. So if you start here and end up there, that's your displacement. Start here and there, that's your displacement. If you go this way, what is your displacement? The 0 vector. You come back to your starting point. If you go this way, your displacement vector is that vector. Okay? A vector from the starting to the final point. Okay? So in 1 dimension, we don't put arrows on top anyway. So the displacement vector is the final position minus the initial position. Okay. Again, in 1 dimensions, the signs can be confusing, so just bear with us. Okay, in 1 dimension, a vector can point, so let's say that's the x-axis. The vector can point in that direction or that direction. So let's say your speed is 5 meters per second here and 7 meters per second here. Okay. We can't assign a number for the direction. So what we use is, we use a sign. Okay. So to indicate vectors pointing to the right, the positive sign tells you that it's pointing to the right, and the negative sign tells you that the vector is pointing to the left. Okay. So in 1 dimension, you're using really only one number to specify the vector, and the sign tells you the direction. Okay. So 1 dimension is funny that way. Distance is a scalar. Okay. Distance is the distance traveled by a particle. So if you go for a walk like that, your displacement is 0, the 0 vector. The distance traveled is 1 kilometer. Okay, so let me draw this. So you go for a walk and come back. Your displacement vector is the 0 vector, but the distance traveled is not 0. Okay. Distance traveled is a scalar. Okay, here's how average velocity is defined. It's the displacement vector divided by the time over which that displacement happened. Again, this is a vector, that is a scalar. A scalar multiplying a vector is a vector. Okay? And the units will be meters per second. Okay. So that's how average velocity is defined. And in 3 dimensions, that'll change to displacement over time, okay? But again, we will be interested in instantaneous velocities, okay, which will be the derivative. And again, that'll come in the next chapter, but that's what we'll be interested in. In this chapter, since we are dealing with one-dimensional motion, there is your velocity. Okay. So here's the average velocity, displacement divided by time. Okay. Average speed, which is a scalar, is distance traveled divided by time. Okay, so let's look at this motion. For this motion, okay, so you started from home and went to the library, let's say, and back. Okay. What is the average velocity? It's displacement over time. And let's say it happened over half an hour. What is your displacement? 0. Okay. So your average velocity was 0. Okay, 0 meters per second. By the way, that's a vector. What was your average speed? Distance over time, you traveled 1 kilometer. Okay, you traveled 1 kilometer. 1 kilometer over half an hour. 2 kilometers per hour. Okay. Neither average velocity nor speed provide details of the trip. Okay, you went to the library and came back, your average velocity was 0. You went to New York and came back, what was your average velocity? 0. Okay. Average speed and average velocity are, by the way, not related. Okay, so you can see that you go to Palm Coast and come back, you go to New York and come back, your average velocity is 0, but your average speed could be anything. Okay, so those two guys are not related. Okay, this is what we're interested in, instantaneous velocity. Okay. So let's say when you're driving on 95, your instantaneous speed is whatever you see on your dashboard, on your odometer or your speedometer, and you know your direction. You're either driving north or south. Okay, so there was the average velocity, and this is how you learn derivatives are defined. Here's the average velocity. In the limit delta t going to 0, that's your instantaneous velocity, and that's written as dx by dt. Okay. So the average velocity between these two times is the slope of this line. Okay. And as you make the interval smaller and smaller, that line becomes, it progressively goes there, and eventually that line becomes a tangent in the limit delta t going to 0. So this guy, dx by dt, is the slope of the tangent line. Okay. Acceleration is, so average acceleration is change in velocity divided by the time over which that change happened. So if your velocity is not changing, this guy will be 0, and your acceleration will be 0. Okay, so you're accelerating only when your velocity changes. Okay. All right, so let's make sure we understand this. So I'll show you the different kinds of acceleration you will encounter. Are you accelerating?
No. Oh, it's those, yes.
Yes,
accelerating.
I mean, so your velocity is changing, okay, you're accelerating. And in this case, it happens that you're accelerating in the same direction, okay? If the magnitude of your speed is increasing, you're accelerating. And notice, okay, so there's your path, and the acceleration is tangent to the path. When your speed changes, the acceleration is tangent to the path. Are you accelerating? Yes. Why?
You're slowing down.
Yeah, your speed is changing, okay? And in this case, the acceleration vector is pointing in the opposite direction, okay? Still tangent to the path, but if your speed is decreasing, your acceleration is in the opposite direction. And it's also given a specialized name, it's called deceleration, but all right, now you're driving on a circular road, and you see you're driving at constant speed. Are you accelerating?
Direction changes.
Very good. Velocity has magnitude and direction, okay? So you can change the velocity any which way you want. You can change its magnitude, you can change its direction, you can change both. So we just were considering special cases. In this case, only the magnitude was changing, and in this case, only the direction is changing. Okay, you can change them both. And you will learn, in this case, okay, the acceleration is perpendicular to the path. Okay, and if the road is a circular road, or even if it's a curved road, you can draw it as a part of a circle, the acceleration will be pointing toward the center of the circle. Okay? So what kind of acceleration would you call it? It is called centripetal acceleration. Okay? So when the acceleration, the acceleration arises just because of the change in direction of the velocity, then it is perpendicular to the path. When you're accelerating just because of change in magnitude of the velocity, the acceleration is tangent to the path. Okay? And then of course, if you have a combination of the two, then you'll have, if the speed is also changing, you'll have an acceleration in that direction, and in that direction, it'll be somewhere like that. Okay? So now you see, now you know how acceleration can arise. Acceleration, you have non-zero acceleration as long as your velocity is changing. Okay? So average acceleration is change in velocity over time. What we're interested in is instantaneous acceleration. It's average acceleration in the limit delta t going to 0. Okay. And that is dv by dt. So the acceleration is time derivative of the velocity, which is the second time derivative of the position with respect to time. Okay. And again, now you'll understand this example that we've done before. So what did we start off by saying? We wanted to describe motions, okay? And here is a description of one particular motion. Oh, I guess I erased the velocity. Will it remember? No, it doesn't. And the second derivative just means you take one derivative followed by another. You took the first derivative and then take the derivative of the first derivative. Okay, so now we see everything here. There's the motion, there's the velocity, and there's the acceleration. Okay. And sometimes you're interested in the time derivative of the acceleration. I mean, very seldom, but those are high-end jobs. But anyway, that's called a jerk. Yeah, right. Time rate of change of acceleration. All right. Here's the fundamental theorem of calculus, and we're going to use that. Okay, so if you have the derivative of a function and you take the integral of that, so loosely speaking, these two operations are inverses of each other. You took the derivative of that and then you took the integral of that. This integral takes the inverse of that. Okay, so what you get is the function back. And then you're evaluating it at those endpoints. And so this is equal to x2 minus fx1. Okay. So if you have a derivative and you take the integral of that function, what you get is you get the function back. All right, we're going to use that. So we just defined velocity is dx by dt. Okay? And I'm just going to show it to you once. Okay, so here's an equation. And of course, you know in mathematics, if you have an equation, you hit this guy with a hammer, you got to hit this guy with a hammer. So let's integrate both sides. We'll take the integral of that, integral of this. That's integral of a derivative. And from the fundamental theorem of calculus, you just get x t x and evaluate it at t1 and t0 equal to v t dt. I've just changed the notation slightly. So this is x t1 minus x t0. That's this guy. That's the displacement. This is the position at time t1. This is the position at time t0. That's the displacement, and that's equal to that integral. But we saw that that integral is an area. Okay? So that integral is the area under this curve. When you plot velocity as a function of time, this area is the displacement. Okay? Again, we're just showing you this. We won't use this a whole bunch. If you plot acceleration versus time, the area under that curve is the change in velocity. Okay? Okay, so again, when you plot acceleration versus time, the area under that curve is the change in velocity. The velocity at this time minus the velocity at that time. All right, so we've already talked about this. So here's the velocity vector of a car. What do you see about the velocity vector?
Not changing.
It's not changing. The magnitude has not changed, neither has the direction. Okay, remember acceleration was defined as change in velocity over time. And over this time, the velocity has not changed, so the acceleration is 0. For this guy, the acceleration is 0. For this guy, see the magnitude is changing and the acceleration is pointing in the same direction as the velocity. Okay? This guy is slowing down and the acceleration is pointing in the opposite direction. Again, here, only the magnitude of the velocity is changing and the acceleration is always tangent to the path. Okay. We will consider circular motion in the 5th chapter or so. Okay. So when you consider motion on curved paths, what is happening? The direction of the velocity starts changing. Okay. And so we'll consider that later. Okay, the derivative was the slope of the tangent line. Okay, so here is a velocity vector. Okay, the velocity is changing, so the object must be accelerating. Okay, and the acceleration is just the slope of this line, so there is the acceleration. For this guy, the slope of the tangent line is changing. The acceleration is changing. Okay, it turns out that it is increasing linearly. For this guy, he's got a non-zero acceleration. The velocity is changing. Now the velocity is not changing. So the acceleration is initially that and then 0. So here is a very special motion that's dear to us. We'll do a lot of problems where the acceleration is constant. And it turns out this is the only example you encounter. Okay? Well, this and related examples. But a freely falling object has an acceleration of 9.8 meters per second squared. That's the magnitude of the acceleration, and it's pointing downwards. Okay? So when the acceleration is constant, and also if you want, you can change the acceleration, the magnitude of the acceleration, by making this object slide down an incline. And depending on the angle of the incline, you can make that acceleration anywhere from 0 to 9.8 meters per second squared. Okay? When will the acceleration of that object be 0?
When it's 0 degrees.
Very good. Okay? So when the incline has an angle of 0 degrees. And when will it be 9.8 meters per second squared?
90 degrees.
Very good. Okay? So that's one way of changing it. And in fact, we'll do this in the lab today. Okay? All right. It turns out that when the acceleration is constant, the position as a function of time is a quadratic function. Okay, you take the time derivative of that, you get a linear function. Okay, and then take the time derivative of that, acceleration, so just to avoid confusion. So when the position is a quadratic function of time, the acceleration is a constant. Okay, and the graph of a quadratic function is a parabola. Okay, so if this guy is positive, the parabola will open up. If this guy is negative, the parabola will open down. Okay, so we in the lab will show you this. For a constant accelerated motion, we'll plot the position versus time of an object, and you'll see it's a parabola. Okay? So now I'm not going to derive any of this, so we'll just give you these equations. So for motion in one dimension with constant acceleration, this is the displacement as a function of time, or you can think of this as giving the position as a function of time. Okay. This is the position at time t. This is the position of the object at time 0. This is the velocity of the object at time 0, so initial velocity. That's how we write. Okay. Times t plus 1/2 a acceleration t squared. Okay. So this equation gives you the position as a function of time. We don't use this too often, but when the acceleration is constant, the average velocity is just the final velocity plus the initial velocity divided by 2. This is true only when the acceleration is constant. Okay. Here is the velocity as a function of time. And you see velocity is a linear function of time. The acceleration is the slope. And here is the velocity as a function of position. Okay. So as a function of displacement, if you want. If you've traveled this far and that's your acceleration, that's how fast you'll be going, if that was your initial velocity. Okay. So for instance, this kind of stuff is useful for planes taking off runways and stuff like that. If you have a runway that big, and a plane needs a certain velocity to take off. Okay? So you decide if you can take off from the airport or not. And of course, if you can't take off, then you don't land on that airport. Right? So these go through the derivation. I won't worry about that. So freely falling object, what do you think that means? Right, very good. Okay, so here is a freely falling object. Is there gravity the only force acting on this?
Air friction?
Yeah, but that's negligible in this case. Okay? So this is not freely falling. Okay, there air friction was not negligible. The drag was not negligible. Okay. All right, so freely falling object is when gravity is the only force and all other forces are negligible. And the acceleration is a vector pointing downward, and its magnitude is, its magnitude is written as g, and its magnitude is 9.8 meters per second squared. Okay, let's make sure we understand this. So let's say and this will be useful for the next chapter. I draw my axes like this. Okay, so the acceleration due to gravity is a vector pointing in this direction. What is the magnitude of that acceleration? 9.8 meters per second squared. And okay, so and g is 9.8 meters per second squared. Okay, so let's make sure we understand this. We'll write it in vector notation. This is 0i. This vector doesn't have an x component, and its y component is negative gj. All right, how about this vector? Again, this guy has no x component, 0I plus okay. G is 9.8 meters per second. Okay. How about this guy? This guy, the x-axis is pointing this way, so it has an x component, gi plus 0. Okay. All I'm showing you is, you know the direction in which this vector points and you know its magnitude. In different coordinate systems, it has different components. Okay? So a lot of people get confused between plus and minus g and so on. G is the magnitude of the acceleration. And then for an axis pointing up, it's minus g, the y component. For an axis pointing down, the y component is plus g. Okay? All right, guys, that finishes this chapter.